Today we're going to take a look at heat transfer through conduction, and we're going to take a look at some of the basic properties about it that affect the heat flow through a wall system. So if we look at a wall system, it can be defined as a separator. It separates an environment, an interior from an exterior, or essentially there's two different spaces with different temperatures. So we can identify that there's a temperature on one side. So for instance, the interior temperature, in this case, it's written as Ti, and a temperature of the outside. So in this case, written as To. Now, as long as there's this temperature differential, we're going to have the transfer of heat. Heat is going to flow from hot to cold. So as long as that differential exists, we're going to expect that heat is going to transfer through this separator. Now, if we're going to quantify how much heat actually transfers through, it's important to know some of the material properties about this wall system. So one of the most important is the thermal conductivity. And the thermal conductivity is actually a description of how well that material allows for the passage of heat. So if we think of a material like steel, it has a lot of, it has a high thermal conductivity and a lot of ability to pass heat through it quickly. If we compare that to a material like wood or a material like insulation, we're going to see that the conductivity is significantly lower. And the units of conductivity also kind of explain what it's all about. So it's explaining how much energy or heat can move through a meter thickness of this material for a difference in temperature of some amount. So that's the conductivity. So conductivity is important for determining the thermal properties of the wall. And the other thing that's also important to note is the thickness of that layer, the thickness of the material. So if you imagine we have a wall system that is very thick, well, that wall system's obviously going to resist the flow of heat a lot better than if it was a very thin wall. So we also want to be aware of the thickness of this material layer. So the thickness, in this case, we're using the term L, and we'll use the units of meters. So of course, we've got the temperature inside and the temperature outside. And well, with these two, thermal conductivity and thickness, we can actually determine quite a few things. So one, we can determine the U value, or the conductance, and we can determine the RSI, or the thermal resistance. So we're going to take a look at a few examples of this. Okay, so conductance. Conductance sort of defines or describes how much heat flow can occur through a separator of known thickness and conductivity. So the way we actually determine this is through an equation, which I'll draw here. So I can either put U value or conductance. In this case, I'm going to use C to represent conductance. And it's actually equal to the conductivity divided by the thickness. Now, to illustrate this, if we take a material with a specific conductivity and we know the thickness of that material layer, we can actually determine what this conductance value is. So let's take a look at concrete, for example. Concrete has a thermal conductivity of 2.0 watts per meter squared. So if I look at concrete, I can actually plug this in to find my conductance. So I'm going to put 2.0 watts per meter per degree Celsius, and I'm going to divide that by the thickness. So for every application, there's probably going to be a thickness associated with it. In this case, let's assume that the thickness of this wall system is equal to 0.1 meters. So in that case, I put 0.1 and meters. So that is going to be equal, if I do the math, to 20, and I'll do the units here, watts per meter squared degrees Celsius. So this actually tells us for this concrete wall system that we're we're going to lose 20 watts of heat for every meter squared for the temperature differential. So if I were to draw a 1 meter squared area here, within this 1 meter square, we're actually going to lose 20 watts of energy for every degree Celsius in temperature differential. So that would be the difference between the temperature inside and the temperature outside. Now, if we were to take a look at something like wood, and we're to do the same thing, we look at wood. So how do you go? C equals, I look at the conductivity of wood, and it's 0.15 watts per meter per degree Celsius. And I divide that by the same thickness of wood, so we'll use 0.1 meters. Well, that's actually going to be equal to 1.5 watts per meter squared per degree Celsius. So if we compare the two, comparing wood and concrete, we see that the wood has a significantly lower conductance or U value. So the concrete has a high U value for conductance, the wood has a much lower one. And this actually indicates that the wood wall, if we're using a wall made out of wood in this instance, well, it would be more than 10 times more efficient. It would lose significantly less energy due to heat loss than the concrete wall. And that's what the conductance can tell us. And we'll look at this, the value of the conductance or the U value, when we look at a lot of energy related problems within buildings. So determining how much heat loss is going to occur, we're going to look towards the U value for that. So we'll come back to that at another point. Now, thermal resistance. Thermal resistance is actually just the inverse of conductance. So it's just another way of expressing the conductance. So if we have the thermal or the conductance, well, we can actually determine the RSI, the thermal resistance, simply by taking the inverse of that. So that's one way we can find the RSI. We can also find it the same way we found the conductance and just invert those terms. So I'm going to put in RSI is equal to, in this case, the thickness divided by the conductivity. So if we use this equation, we can actually determine the RSI. And let's pull up our materials again, and we'll take a look at wood. No, actually, we'll take a look at concrete again. So RSI equals, so I'll put thickness. We're going to use the same 0.1 meter. And the conductivity in this case is 2.0 watts per meter Celsius. Now, if we solve for this, get about 0.05. And then it becomes meter squared degrees Celsius over watts. I got that right. Yeah. Okay. And the units of this are very more challenging to understand, but essentially what it's describing is the material or the separator's ability to resist the flow of heat. So a higher RSI that is higher, so a larger RSI, it's actually a good thing. We want the RSI to be high. So if we were to do this with, say, wood or insulation, we're going to notice that this RSI is not going to be this small number here of 0.05. It's going to be significantly larger than that. And that's a good thing. So we want a high RSI. And, that's different from the U value, where for the U value, what we just calculated previously, we actually want a very low U value. Okay, so here's a question for you just to test what you've learned so far. and that is, what is the U value of a wood wall that is 30 centimeters thick? Okay, so you've got to find the conductivity and the thickness, determine the U value. And the second one is, what is the RSI of an expanded polystyrene foam layer that is 0.05 meters thick? So again, using the conductivity and the thickness, you can find the answers to both of those. Okay, now seldomly do we have a wall system made of just one material. So commonly we're going to have multiple layers. So it could be a layer of concrete, followed by insulation, followed by drywall. And that would be a pretty simple example. So you might have 3 different layers. You might have significantly more than that. In this case, though, each layer will have an RSI. So you can find the RSI for layer 1, RSI for layer 2, RSI for layer 3. And the total RSI, so the RSI total, is actually equal to the sum of all RSI layers. So for all the RSI layers, all the layers, we're going to have to add up those RSIs. So there'll be, in this case, the 3 layers to add, and that'll give us the total RSI. So very simple. Now, when it comes to the U value, and if you want to know the sum of all the U values, so the U value of that whole system, you might think that you can just take the U value of each layer, but you cannot. So you cannot add the U values. It will not give you the right answer. You can only add the RSI to find the total RSI. So if you need to find the total U value of that wall system, well, what you'd have to do is take the total RSI, you take the inverse of it. So you go 1 divided by RSI total. So that's just a tip there. And here's a question to just test your understanding. So we have a wall system, and it's asking you, what is the total RSI of this wall system? It's got 3 layers. So it's got 10 centimeters of concrete, 5 centimeters of EPS, and 10 centimeters of concrete. So using the past approach, find the RSI of each layer, add those together, and get your total RSI. Okay. Now, one thing to add just slight amount of extra complexity to it is what's called an air film. Now, the thermal resistance is mostly provided by the separator, by the wall itself. However, if you think about how heat transfers from the surface of that separator to the environment, well, in our, let's say this is the interior, put TI, we've got air that's flowing around and there's convection currents. And as that air gets nearer to the wall, there's actually this layer of air that clings to the wall and it doesn't move too much. So it's a very still layer of air. And this is known as an air film. So air film. And there's actually an interior air film. So that would be on the interior surface. And there's also going to be one on the exterior. Now, these layers actually provide a little bit of thermal resistance, and they've been calculated. So if we look at a table from ASHRAE here, if we look at the surface, so in this case, we're going to have to look at the surface and vertical because we're dealing with a wall system here. So we're dealing with a vertical surface of still air. and the direction of flow is horizontal. That's the path perpendicular, which heat is going to transfer through. And we're going to look at these numbers here. So it says 8.3, 4.2. Well, okay, 8.3 is what we want to look at. The surface emissivity, I won't get into it, but almost all building materials are going to have a surface emissivity of over 0.8. So we'll just cross those ones out. And we'll use this value here. This is the surface conductance. So this is essentially that portion of the U value, the watts per meter squared degree Kelvin or Celsius. And this 8.3, so if I put the conductance for interior air film, C interior air film is equal to 8.3. Well, if I want to know the RSI of that interior air film, I just have to take the inverse. So 1 divided by 8.3, right? Because we're converting conductance to RSI. So if I take out the calculator and I put 8.3, and I inverse that, I get 0.12. Meter squared per Celsius watts. Okay, so that's the RSI of the interior air film. Okay. And on the exterior, if I were to look at the exterior, the conductance of the exterior, so exterior air film, well, I'll look down here in this table, and there's a few different values, but let's assume it's winter time and the air or wind is blowing at 24 kilometers per hour. So this is an assumption. And they're using a value of 34. Well, to find the RSI of the exterior air film, it's going to be equal to 1 divided by 34. And that is equal to 0.029 or 0.03. Okay, so that's the RSI for the exterior air film, the RSI of the interior air film. And now that we found that, we can actually go back to this question. And here we have our 3 different layers. So we've got a layer of concrete, insulation, and then concrete again. But we also have a layer of, so it's not just layer 1, 2, and 3. We also have, we can call this layer 0, the air film for the exterior. And we also have the air film for the interior. So that would be, in that case, 4. So 1, 2, 3, 4 different layers that we've got to consider. And so the question is asking us now, considering the air film, what is the total or the true effective RSI? So the true effective RSI, and we just follow the same process to determine that. So that should be pretty straightforward, and we'll take a look at the answer after you give it a try.